In this video, we'll be learning how to prove that two functions are definitely inverses of each other. So let's begin by reviewing just what inverses are in general. Remember that inverse functions are two functions that are reflections of each other over the line y equals x. So here you can see you have the line y is equal to x, and you can see if you were to fold over that green line that the blue and the red line would line up directly on each other. So they are reflections of each other over that line. Now what's really interesting about their tables is we can actually tell just from looking at a table whether or not two functions are in fact inverses of each other. So if you look carefully here, you'll notice that these two tables are really just x and y values that are flipped, which I find really interesting, that inverse functions, because they're reflected over this line right here, because of this reflection, all that happens is their x and y values become opposite. So here you'll notice in the first point, x is -2, y is -1. And then you'll notice in the second point down here, x is -1, y is -2. If you don't believe me, go look at the graph. X is -2, y is -1, that's a point here, and then x is -1, y is -2 is a point here. So these points are reflections of each other over that line y equals x. And if we continue to look at those types of points, so say we go to -1, 1, and then we go to 1, -1. Again, points that are x and y values flipped, and they are in fact just reflections over that line y equals x. So the first way that we can verify that two functions are in fact reflections are just by looking at the table, and we're looking for x and y values that are essentially the opposite, depending on which table you're looking at first and second. So that's the first way that we can verify that two functions are inverses. We just look at their tables and we notice that their points are just x and y values flipped because of this reflection over y equals x. Now, while that table trick is really helpful, we don't always have access to the table for those two functions, nor do we necessarily want to sit there and have to calculate all of the points for a table for each function. So we have to find another way to verify that two functions are in fact inverses of each other when we do not have a table. And what's cool about inverses is that they have another property. Now I know this property looks confusing at first. I'm going to explain it to you in a second. But what this says is if f of x and g of x are inverses, then f of g of x is equal to x and g of f of x is equal to x. Now I know this looks confusing, and I'm going to break down what this is actually saying for you in just a moment. So let's look at a different example first so we can figure out what on earth this notation means. So let's say for a second, let's say f of x is equal to 2x plus 3. That's what we saw on the previous page, right? And let's say that we're going to find f of 2. Now, what you know about this notation is that when we replace x with 2, what we're going to do is we're going to go to every x in this particular equation, and we're going to replace x with 2. That's what this notation is saying. F of, and we replaced it with 2, we're going to go wherever x is, and we're going to replace x with 2. So we would take 2 times 2 plus 3. That becomes 4 plus 3, which would be 7. So this is what we already know about function notation. We know that if we replace this x value with something else, that something else goes in place of x. And that's the same idea that's happening over here. Well, I know there's a lot of parentheses here, and there's kind of an extra one as well there. So there's a lot of parentheses going on here. What this is really saying is we have f, and then we have g of x on the inside, if you look carefully. That's what this is really saying. And this one over here is saying g, and then we have f of x on the inside. So in this notation, essentially what this is saying is if we take whatever g of x is equal to and we replace it in place of x in the other equation. So wherever x is, we're going to place whatever the entire function of g of x is. If we do that, what we're saying is that if we solve it and simplify it down, we will get x. So let's actually see this in action, and let's actually go back to that example on the previous page. So we knew that f of x was equal to 2x plus 3, and we knew that g of x was equal to x minus 3 divided by 2. So let's actually walk through this process here. So let's do f of g of x and verify that it does in fact equal x. So we're going to take our f of x function, which is right here, and every time we see an x, we're going to replace it with all of g of x. So I'm going to do 2 parenthesis, because that's where I'm replacing my x value. And notice that I'm going to take where x was before, so x was next to the 2, and I'm going to replace it with x minus 3 divided by 2. So hopefully you can see that I took where x was, and I replaced it with this entire function called g of x. And g of x was equal to x minus 3 divided by 2. Now, what hopefully you're noticing is that you have a fraction here. And here you have 2 over 1, and then you have the fraction x minus 3 is in your numerator over 2 plus 3. That's what's really going on right here with this multiplication. Now, what I'm noticing right off the bat is I have 2 over 1, and then I have a 2 in my denominator over here. Well, what's really cool is if we simplify this and we write 2 times x minus 3 over 2, we can see we have 2 over 2. That simplifies down just to 1. So this becomes x minus 3 plus 3. Well, the negative 3 plus 3 equals 0, so we're just left with x. So notice here that if we replace x in f of x with g of x, when we simplified it down using the properties that we know, we were left with just x. So now let's repeat this with g of f of x the other way around here, and let's verify that that one also equals x. So we can verify that these two functions are in fact inverses of each other. So let's walk through that process again. So here we're going to take the function g of x this time, and every time there's an x, I'm going to replace it with f of x, which is 2x plus 3. So here I have, let's see, x is first, so I'm going to put in parentheses 2x plus 3, and then there's a minus 3 there, all divided by 2. Well, I don't need those parentheses because there's no coefficient or anything out in front of them, so I have 2x plus 3 minus 3 all over 2. Well, plus 3 minus 3 equals 0 up in that numerator, so I'm left with 2x over 2, which simplifies down to x. So because both f of g of x and g of f of x happen to equal x, these two are in fact inverses of each other, these two functions right down here. So let's verify a couple of more functions. Let's see if the two functions we have are in fact inverses of each other. So remember, if these are inverses of each other, f of, remember g of x going in the middle there, is going to equal x, and g of f of x is going to equal x. So we have to verify that both of those situations are happening. So let's start with f of g of x. And remember, what this means is that everywhere where there's an x in f of x, we're going to replace it with what g of x is equal to over here, which in this case is x plus 1 divided by 3. So if we do that, we start off with a 3, and then we have what x is, which is going to be g of x, so x plus 1 divided by 3, and then the minus 1 on the outside. So just like last time, I'm going to turn this into 3 over 1 times, that's x plus 1 over 3, so that becomes 3, and there's still that negative 1 out there, but there's 3 times x plus 1 over 3 minus 1. Now I can see the 3's are going to basically simplify down to 1 because that's 3 over 3. So then I'm left with x plus 1 minus 1. The plus 1 minus 1 becomes 0, so I'm just left with x. So I've verified that f of g of x is equal to x. Now if we take a look at this second one, let's do the same thing. So now we're going to take g of x, and wherever x is, we're going to replace it with 3x minus 1. So we have g of f of x that we now need to test. So we have 3x minus 1 plus 1, all divided by 3. I don't need those parentheses because there's no coefficient or anything there, so I have 3x minus 1 plus 1 over 3. These two together become 0, so I have 3x over 3. That simplifies to 1, so I am just left with x. So what I can conclude from looking at these are that f of x and g of x here are inverses of each other because f of g of x equals x and g of f of x is equal to x. So now let's test out these two examples in example 2. So let's start with f of g of x. So we're going to put all of function g inside of x here. We're going to use some parentheses too just to make sure we don't miss a detail. So here I have 8, and then I'm going to put parentheses where x is. I have the cubed root of 2x, and then it's all cubed. So to start off this problem, the first thing I notice is that I have a cubed root inside of a cubed function. And I know that roots and powers undo each other. So what's really cool here is because we have a cubed on the outside and we have a cubed root on the inside around everything, these quickly undo each other and we're just left with 8 times 2x. Because these undo each other and they're gone. And then if we simplify this further, this equals 16x, which wasn't what I was expecting. I was expecting it to equal x, so I'm thinking these aren't inverses, but let's just take a look at g of f of x and see what happens there to make sure. So here we have g of f of x. So everywhere where there is an x here, I'm going to put this whole function. So here I have the cubed root of 2 times 8x cubed. Well, this becomes the cubed root of 16x cubed. Well, 16 isn't a perfect cube, which is unfortunate, but this x cubed is a perfect one. So x cubed and the cubed root, I can pull the x out in front. Then I can break 16 down into 8 and 2. The cubed root of 8 is 2, so I get 2x cubed root of 2. Now when I look at these two examples, what I notice is that neither one of them equals x, which is a problem. If these are inverses of each other, this is going to equal x, and this is going to equal x. But this one equals 16x, and this one equals 2x, the cubed root of 2. Because of that, these are not inverses of each other. So one final example here. So let's take a look at f of g of x to start to verify that these are in fact inverses. Remember, as we do that, we're taking all of g of x and we're replacing it inside of x in this particular function. So we have the square root of 4 times, I know this is going to get messy, 3x squared plus 5 over 4, all minus 5, all divided by 3. So I know that this looks messy. Just give it some time, because if they are inverses, this is actually going to work out really, really nicely. So I'm going to scroll down just a bit. So if I go from here, first thing I'm going to try to deal with and get rid of is this fraction. What I notice here within this fraction is this becomes 4 over 1, right? So we get 4 times 3x squared plus 5, all in parentheses, over 4, then that minus 5 on the outside, all over 3. What I notice if I look closely in here is I notice that I have a 4 over 4, which becomes 1. So because of the way that, inverse functions work, if they are inverses, they're going to simplify out really nicely. So that becomes 1, and inside of my fraction here, I get 3x squared plus 5, the denominator is now gone, then I have that minus 5 on the outside, all over 3. So that worked out really nicely. Now if I look here, plus 5 minus 5 in the top of that fraction becomes 0. So I'm left with 3x squared over 3. And then I notice, okay, I have 3 over 3. Well, that becomes 1. So now I'm left with the square root of x squared. And because I have the square root of x squared, the square root, this is really a 2 here, these undo each other because it's a square root and a squared, so this equals x. So even though those looked pretty complicated, we still ended up with f of g of x was equal to x, which is what we were looking for. So now to verify that these are in fact inverses of each other, we need to verify that g of f of x is also equal to x. So let's do that next. So let's start off with g of x here, and we have 3, and then I'm going to leave myself a lot of space here to put f of x in there, squared, plus 5, and then that whole thing is over 4. So here I can see that if I put f of x in there, it's the square root of 4x minus 5 all over 3. Now, to start off right off the bat, what I notice is I really have a square root and a squared here. And what's really nice is because the square root is around this entire thing inside of parentheses, and the squared is outside of the parentheses, they immediately undo each other and they are gone. So what we're left with here is 3 times in parentheses 4x minus 5 over 3 plus 5 all over 4. So that's the first piece I'm able to undo. Then what I start to notice here is I might be able to undo these right off the bat as well. So if I do 3 over 1, this is going to become 3, and then it's going to be 4x minus 5 in that numerator over 3 plus 5 over here all over 4. Well, if I notice 3 over 3 is 1, so all of a sudden 3 over 3 becomes 1. This just becomes 4x minus 5 plus 5 up in the numerator all over 4. Well, negative 5 plus 5 is 0, so those undo each other, and we're left with 4x over 4, and then 4 over 4 is 1, so this simplifies down to just x. So at the end of the day, we have g of f of x also equal to x. So what we can say is these two functions are inverses because f of g of x equals x and g of f of x equals x.